but now we're going to talk about sequences and summations. All right, all a sequence is, it's just a function from some subset of the integers. Usually the subset is like 0, 1, 2, etc., or 1, 2, 3, etc. Usually that's the subset we pick to a set S. All right, so what's a sequence look like? It looks something like this. Say, here's 1, here's 2, here's 3, ellipsis. Over here I have a set S, which is made up of a bunch of stuff. What's in it? Numbers? Nah. Students? Nah, don't care. All I'm restricting it to is the left-hand side is normally the counting numbers. And then what I do is I have a function, say f, that I do this sort of mapping. Right? 1 goes there, 2 goes there, 3 goes there. And so what happens here is this function is f of 1 gets mapped somewhere, f of 2 gets mapped somewhere, f of 3 gets mapped somewhere, and f of 4 gets mapped somewhere. What's nice about this is because there's order to my domain, I can go ahead and order my function. I can say, where does 1 go, where does 2 go, where does 3 go, where does 4 go? And I can just simply do that. Now normally when we write, where did 1 go? Where did 2 go? We could go through a room and say, okay, you're first place, second place, third place, fourth place, fifth place. Just go through there and you just label everybody. And I can look at this and say, these are all ordered pairs, right? This is 1, f of 1, and then 2 has been mapped to f of 2, right, etc. But since 1, 2, 3, 4 already has order, can I simplify what I just wrote? Don't write 1, 2, 3, 4. Wouldn't it be enough if I said that I go through here and say you're first, second, third, fourth, fifth? I could just simply say, how about just line up at the front of the room? And we would all know who's first, second, third, fourth, fifth by just simply looking. Why do I have to write the domain elements? Why not just write the images? And if we just write the images in terms of notation, normally what we do is say, okay, fine. 1 has been mapped to f of 1. We would just simply rather write f sub 1. What does that mean? 1 has gone to this f sub 1, whatever it is. Where's 2 gone? I'm just simply going to write f sub 2. And then I'm going to put them in this order, and the order I call it would be simply, the sequence is simply f1, f2, f3, f4, dot, dot, dot. The sequence is just simply the collection of the images in order. It's like, everybody go to the front of the room. You're first, second, third, fourth, fifth. We all know. Where did 1 go? First person. Where did 5th go? 5th person. It's easy. So this allows us to take this sort of notation. Normally when we have a notation like this, in terms of sequences, is we'll write things like this. This is a sub n, where this is some sort of the rule to make the sequence. Normally this rule is just simply what? It's the function, right? That's what it is. So let's do some examples that everybody should know. 1, a geometric sequence. If you have a geometric sequence, what you're really saying is the rule that you follow is some number times r to the nth power, where we start off at 0 and then move on. Example in specifics. Let's say what would be 3 to the negative 2 to the n, where n is equal to 0, 1, 2. What would that generate? What would the sequence be? Plug a 0 in. What do I get? 3 times 1, which is 3. Plug a 1 in. What do I get? Anybody? Negative 6. Plug a 2 in. What do I get? Plug a 2 in, that would be 4 times 3. I get what? 12. Plug a 3 in. What do I get? Negative 24. Dot, dot, dot. In terms of sequences, you need to be able to do two things. I should be able to give you the function with its what's going in, what's its inputs, 0, 1, 2, 3, and then you should be able to give me the outputs. We usually want to be able to go from, can you go from the rule to the sequence? And on the other hand, could you go backwards? Sequence to rule. If I gave you the numbers 3, negative 6, 12, negative 24, could you figure out that the rule is what? 3 times negative 2 to the nth power, where n is equal to 0, 1, 2, 3. We need to be able to do these two things. So we're going to learn lots of pattern recognition. What do you notice about geometric things? What happens if I divide everybody by his neighbor? What is 6 divided by 3? If we go the other way, that'd be like 3 over under 6 would be a half, 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 right? If we were going this way. But going this way, 6 over 3 gives me what?
Negative 2.
Negative 2. What's 12 over negative 6? What's 24 over 12?
Negative 2.
Why? That's what happens. Every time we have something, we get another negative 2 multiplication. So if you divided neighbors and you got a constant, you know it's automatically geometric. Another one that we should know, arithmetic. Arithmetic sequence, the a sub n is equal to some sort of a plus d times n, where n is equal to 0, 1, 2 as well. What happens here? Let's do a specific example. What if I had 1 plus 3n, where n is equal to 0, 1, 2, dot, dot, dot? What sequence would this form? Plug a 0 in, what do I get? 1. Plug a 1 in, what do I get? Plug a 2 in, what do I get? All right, plug a 3 in. What do I get? What do you notice about each of these neighbors? If you divide, you don't get a constant, but what would happen if I subtracted? They're all 3 apart, right? So if I subtract and they're all 3 apart, then you automatically know, oh, arithmetic. If you divide and it's a constant, geometric of some sort. You just got to figure out what the numbers are that make it. If I just gave you a sequence and you didn't know if it was arithmetic or geometric, what should you do? Subtract, see if it's a constant. If it's not, like for example, what happens if I subtract these? Subtract those. Ignore the sign for a second. What's 6 minus 3? What's 12 minus 6? What's 24 minus 12? All right, it's not a constant, so you definitely know it's not arithmetic. Then you move on to dividing. Oh, it's a constant. It's geometric. All right, another one that everybody should know would be a sub n is equal to n squared, where n equals 1, 2, 3. What's that sequence? Plug a 1 in. Then 4, then 9, then. Everybody should recognize the squares, or 1 off of the squares, or 2 off of the squares. Right? You should be able to recognize squares, close to them. What do I notice about the squares when I subtract? We already had a proof for something like this. Subtract the squares. What do I get? What's 4 minus 1? 3. What's 9 minus 4? 5. What's 16 minus 9? 7. If they're all, 3, 5, 7, 9. Ooh, this is a square somehow. There's a square involved in this. We should be able to recognize the squares. We should be able to recognize the cubes. What's the sequence of the cubes? What's 1 cubed? 2 cubed? 3 cubed? All right, we should be able to recognize a little bit of the sequence of the cubes, a little bit of the sequences of the squares. we should be able to recognize just a straightforward power. What is that sequence? Plug a 0 in. 1. Plug a 1 in. Next. It's just doubling, right? If you notice it doubles, it's a 2 to the n. If you notice it triples, it's a 3 to n. We should know those. Other ones that we should know: 6. A sub n is n factorial, where n is equal to 0, 1, 2, 3, etc. What's this sequence? 1, 1, 2, 6. Next. We know that. 24. What am I doing each time? Start off at 1, and then what do? Multiply by 1. Then I multiply by 2. Then I multiply by 3. Then I multiply by 4. If I gave you the sequence, how could you know it was a factorial? What's 1 divided by 1? What's 2 divided by 1? What is 6 divided by 2? What's 24 divided by 6? You do your divisions, and what do you notice happens? 1, 2, 3, 4. Oh, everybody's multiplied by the next int. This is factorial. Somehow. And if it's like close to that, and then you start to play around with it. This is one of the things where we talk about pattern recognitions of numbers. How many of you guys just like to play around with arithmetic? You just do numbers all the time. You just walk around and you do doubling. How high can I double today? I'm going to walk to class. I'm going to see how high I can double. 2, 4. Now what? 8. Now what? Right? Can you do multiples of 2? Can you do multiples of 3? Can you do them in your head? If you don't do it, you're not going to see the pattern. And so these are sequences that we should recognize. All right, there are some sequences, and I'm going to split between two things. An open form of a sequence versus a closed form of a sequence. Closed form of a sequence is pretty easy. A sub n is equal to 2 to the n, where n is equal to 0, 1, 2. And then this thing spits out 1, 2, 4, 8, 16, ... So the sequence itself is the numbers of where you've gotten to. The formula is closed form. Closed form just simply means that you have, closed form simply says you have a nice, clean function. Number comes in, number comes out. Where does 100 go? 2 to the 100th power. Where's 1,000 go? 2 to the 1,000th power, right? We can immediately get to the value. The idea of an open form, on the other hand, is what's called a recurrence relation or inductive. So recurrence relations are this. The way this works is you start off and you say you have a basis. Say the very first number is 1. We start off with a beginning. I tell you the first numbers of the sequence, number or numbers. The second thing we do is we have the recurrence relation. Now a recurrence relation is simply going to be this. New values are equal to some rule on old values. So for this example here, I could say that, oh look, my new values, a sub n, are always going to be twice a sub n minus 1, which is my old value when n starts at 1, 2, 3, etc. And so that would be my recurrence relation. How do recurrence relations work? You have your first number, 1, and then you look at the rule. What does the rule say? A sub n is twice a sub n minus 1. Well, what's a sub n minus 1? It's the guy in front of a sub n, right? If this is a0, then that would be a1. That means a1 is twice a0. What's twice that? 2. What's a2? It's twice a1, which is what? 4. Does that generate the same sequence? Yeah. What's twice 4? 8. What's twice 8? 16. generates the same sequence. So what's a closed form? Function. What's an open form? Recurrence relation. Why do I have recurrence relations? Well, sometimes we can't figure out the closed form, and sometimes it's easier to think about building new stuff from old stuff. Let's say I start off with an example. Instead of using A's, I'm going to use, let's say that my 0th object is 0, and my 1 object is 1. So 0 has been mapped to 0, 1 has been mapped to 1, and this is my basis. I give you the first two values. But now, new values are the value in front plus the value in front of that. Since 0 and 1 is already handled, where does 2 go? Well, let's look at this. Here's F0, so what's my sequence? It's going to go F0, F1, F2, F3, F4, dot, dot, dot. What is F0? 0. What's F1? 1. What's F2? 2. Who's before 2? 1. Who's before that? 0. Okay, what's F0 plus F1? F3 is F1 plus F2, which is 2. What's F4? What's 1 plus 2? 3. What's the next guy? What is the sequence called? Everybody should recognize this. It's the Fibonacci numbers. The Fibonacci numbers are, take two values, right? Add them together to get the next. Now I don't have to write the recurrence relation in this form. I just have to say, you would look at this and realize n minus 1 is before n, and n minus 2 is before n minus 1. You could write that however you want. You could write, that's n plus 2, that would mean n plus 1, which would mean that would be n. All it has to tell you is that two beside each other add to the next. On the other hand, we could play around with it. If 2 add to the next, what would be the subtraction of 2? If this plus this equals this, what would be this minus F2? It'd be F1. So if you'd subtract 2, you'd get the 1 to the left. Well, what if you subtracted these two? What would you get? The 1 in the middle. Those are all the same rule, right? What's nice about recurrence relations is we can work on this. This particular induction, if you need more, if you need the guy right in front of you, like the one we did above, that's usually called weak. If you need more than that, we normally call it strong. In the end, it's induction. So what should we be able to do? We should be able to, given any rules, an inductive rule, a closed rule, what's the list of numbers? From a list of numbers, could you guess, try, figure out the rule? So that's one way we could try to do it, is to simply guess it. So how can I go from open into closed? One, this is simply, we could do things like, can we guess? Just find a closed rule. It's like, all right, I think it might be this. Give it a shot. See if it works. All right, the other technique is called forward substitution and back versus backward substitution. All right, so let's pick one that we already know. I'm going to start off at 1, and a sub n is twice a sub n minus 1. Is my rule, where n is equal to 1, 2, 3. I already know what the closed rule is. This will be 2 to the nth power. All right, now if I didn't know the closed rule, what could I do? The idea of forward substitution is to do this. Is to say, okay, A0 is 1. Okay, A1 is twice A0, which is just simply 2 times 1. But A2 is twice A1, but that is actually, I'll just leave that as a 2. That's equal twice 2. Hey, that's a 2 squared. What's A3? That's twice A2, but I already found A2. I could have written 4, but it's better to write it as an exponent. And that's equal to twice 2 squared. Hey, that is 2 cubed. What is A4? That's twice A3. That's what the rule is, right? The next is twice the previous. But what's A3? I found it. It's 2 cubed, so that's twice 2 cubed. That is 2 to the 4th. If you continued this pattern, what would be A to the n? 2 to the n. Done. That's forward reasoning. I mean, just go forward, plugging it in, but what you cannot do is simplify your number because you lose what the pattern may be. You have to leave it as in like exponent form or addition form to trying to get a formula out of this. You're trying to find a formula, not the number. Right? What would be backwards? So that's forward. Backward substitution. Backward substitution is this. A sub n is twice a sub n minus 1. But what is a sub n minus 1? That's twice a sub n minus 2. So that tells me that a sub n is twice a sub n minus 2, which is 2 squared a sub n minus 2. But what's a sub n minus 2? That's twice a sub n minus 3. Oh wait, that's 2 cubed a sub n minus 3. Well, what's a sub n minus 3? That's twice a sub n minus 4. And that's 2 to the 4th a sub n minus 4. All right, how long will that go? Does everybody see the pattern? That number is always that number. How low does n minus whatever go? What's the smallest that we have? A0. What would I have to take away so that this last thing was A0? Everybody see the pattern? Right? That was a 3, n minus 3, 4, n minus 4. The most I can take away is n, so that is equal to 2 to the n times a0. But in my original problem, what was a0? What was the basis? 1. That's equal to 2 to the nth times 1, which is equal to 2 to the nth. So a sub n is equal to 2 to the nth. Same formula. Which makes more sense to you? Do you like thinking forward, or do you like thinking backwards? Doesn't matter. It'll get you to the same place. So that's how we go from open to closed. Going from closed to open usually requires just simply creativity. What's going on? I'm always adding the next. I'm multiplying by something. Geometric and arithmetic is not too bad. All right, so that's sequences.